Thank you, and I thank the organizers for the invitation. I've prepared some slides, but if you have any questions, just hesitate to stop me and to ask me to explain something else, and we have a blackboard, and we can change the. Yeah.
Instead of pointing to the screen, can you just use your mouse? Otherwise, on record the mouse, you can just use the mouse so that yes, so that whenever exactly, so that really it's because otherwise it doesn't get recorded. Yeah, but if you need to point to something, just point with the mouse.
Okay. Well, so this talk is a kind of a bridge between the tutorial done by Alexander Shannon yesterday and the talk of Marius Ziemand this afternoon. And also, it's kind of advertisement of the upcoming 2 weeks of the Nexus, which will be devoted to the information inequalities. So my plan is, first of all, to advertise the idea of the parallelism between two kinds of information theory, between the classic information theory by Shannon and the algorithmic version of information theory by Kolmogorov. And we will see some parallelism, and we will try to use somehow the idea of this parallelism. So first, I will probably repeat some things from yesterday's talk of Sasha. One of the very first of the basic papers on algorithmic information theory was entitled 3 Approaches to the Quantitative Definition of Information. So what are these 3 approaches? The first one is probabilistic. It's the theory of Shannon, and in this theory, we measure the amount of information in a random variable, and this measure is the standard Shannon's entropy. In the second approach, we measure Kolmogorov complexity, which is the amount of information in some constructive object, typically in binary string. And another approach is combinatorial. It's less popular, and it is not very common. So it's not quite clear what should be the standard measure of information here. Probably it should be this Hartley's information defined in 1920s. Why should we keep in mind these 3 approaches? Why should we think of them, even if you work in one specific area, say in Shannon's theory or in Kolmogorov complexity theory, why should you think of another one? In fact, you can steal some theorem from one domain and translate it to another one. So if you see some nice theorem and in algorithmic information theory or in probabilistic information theory, then it's quite possible that you can transpose it to your domain and prove a counterpart of this theorem for yourself. Another reason is it seems that if some theorem has different versions in different information theories, then it's probably really the right theorem. It makes some sense. And also, it could be useful to understand the same phenomenon, the same mathematical result from different points of view. And especially, it's interesting to not miss the special cases when this parallelism doesn't work, when something is broken. Then we should pay attention to these special theorems and understand what is wrong and why it happened that this parallelism cannot be extended to some results. Well, I'll start very slowly with the basic definitions, so the things you probably know. So what is the measure of information or the measure of uncertainty in an object. And what kind of object should we take? In Shannon's theory, we take a random variable and measure its randomness, its entropy, just as Shannon proposed. In Kolmogorov complexity, it seems that the things are pretty different. An object which contains information is, say, a binary string, or some constructive object that can be encoded as a binary string. And the measure of information of this object is the minimal length of a program that can print this string. And in Hartley's case, let us say that combinatorial entropy of an object of a finite set is just a logarithm of the cardinality of this set. It's a pretty trivial thing. Indeed, if you want to encode an object in a finite set of size n, then you need log n bits to provide an index of an element. So here, the things are pretty trivial. Let's go further. In Shannon's theory, we have a conditional entropy. There are several equivalent definitions, but probably the most natural is this one. We fix different values of beta. For each fixed value of beta, we have a conditional distribution for another variable alpha. So we have a conditional entropy.
It should be beta there, I guess.
Where?
Probability of bi equals to beta.
Yeah, should be beta.
You should point with a special device also.
Okay. Okay, no, it's so simple that I think everyone understands where is the mistake. Kolmogorov complexity, Sasha explained it yesterday. We measure complexity of A given B is a minimal length of a program that prints A given B as an input. Or it's also equal to the difference between the complexity of the pair AB and complexity of B. Well, with this logarithmic precision. And what should we do in Hartley's case? If we have some bidimensional set A, then how much information do we need to reconstruct B given A, or to reconstruct A given B? Well, we should measure the vertical, or respectively the horizontal section, and count the number of elements there, and again take the logarithm. So again, everything is pretty trivial.
And take the maximum.
And take the maximum, yeah. We should take the maximal vertical section for the conditional entropy of B given A, or the maximal horizontal section for the entropy of A given B. Yes. Well, how to measure the useful information, the amount of information in something about something? Well, the information in alpha about beta is measured by Shannon like this, so everyone knows that. Or it's equivalently the difference between the sum of two entropies for alpha and beta, and the entropy of the pair. And the same things are defined for Kolmogorov complexity. And again, the equation is for two equivalent definitions, holds up to a logarithmic term. Hartley, I think you don't want to see this formula, but you understand what I could say here. So if you want to explain it somehow naively in a philosophical mood, then you could say that Shannon's entropy, Shannon's approach is a measure of average complexity, average number of bits that you need to describe something. In Kolmogorov's case, you measure somehow algorithmic complexity, and in Hartley's approach, you measure somehow the worst case complexity. Well, let's look again on some basic, some trivial properties. So we have this equation for Shannon's theory and this inequality. So the equation is just trivial, follows immediately from the definition, just some algebraic calculation, which is straightforward. The inequality is pretty simple, but not that trivial. It requires to use a Jensen's inequality or something similar and concavity of the logarithmic function. In Kolmogorov's complexity, even this equation is not that simple. It's, this is the theory, the Kolmogorov-Levin theorem, which requires some argument. But this inequality is pretty simple. In Hartley's case, well, everything here is trivial, so probably you're asking yourselves, why should we care about this combinatorial approach if everything is so stupid and so trivial? Well, let's look on some other example, less trivial. It's, maybe we will even prove this inequality if you want. It's pretty simple to prove it. In Shannon's case, in Kolmogorov's case, and not surprisingly, there is a similar statement for Hartley's entropy. Here, the inequality for Hartley's entropy claims that if we have a three-dimensional set, some A, and we take three projections on three coordinate planes, then the square of the cardinality of A is not greater than the product of the sizes of these three projections. And this statement is not that trivial. If you want a social experiment, you can give this inequality to your students as an exercise and see the results. If you don't explain in advance that it is connected somehow with Shannon's entropy, it's not that simple. It's possible to prove it without entropy, but it's not that trivial. And in fact, it can be shown that every inequality for Shannon entropy or for Kolmogorov complexity can be somehow translated in a language of Hartley's information. And in some cases, we get something really non-trivial. So when we talk about the inequalities, the parallelism between these three approaches is quite straightforward, quite evident. So we have all these inequalities for Shannon entropy and similar inequalities for Kolmogorov complexity. And you see just syntactically, it's almost the same thing. The difference is that for Kolmogorov complexity, we should always add this logarithmic term. Yeah, and to not mix the information for Kolmogorov complexity and for Shannon entropy, I will write the indices IS and IK just to distinguish between the mutual information for Shannon and for Kolmogorov.
And I guess it should be C everywhere. C for Kolmogorov because it's.
Yeah, you're right. Yeah. Yeah, of course it should be done. C, yeah. Okay. Well, and in fact, this in case of inequalities, this parallelism can be established formally. Are there any misprints here? No, I think here is correct. Well, it's a general rule. If you have some linear inequality that is valid for Shannon's entropy, then the same inequality must be valid for Kolmogorov complexity with logarithmic precision, and vice versa. So exactly the same inequalities are valid for Shannon's information theory and for Kolmogorov's information theory. I will not talk about the proof of this theorem. I will not need it. But I will use this equivalence theorem as a kind of metaphor, as a simple example of parallelism between these two approaches. Just one remark for experts. If you look into the proof, then it turns out that the same things works if you put here, instead of the logarithmic term, something greater than logarithm, something like square root of n, some square root of complexity involved in the inequality. So it means that the information inequalities with a logarithmic residue term are with square root residue term, and any other reasonable residue terms, they are all the same for Kolmogorov complexity. So there is no inequality that would hold for Kolmogorov complexity with a precision square root of the complexities, but not with the logarithmic one. Okay.
Just in the sublinear term.
I'm not sure about terms which are less than log n. Certainly there are inequalities that are valid with a constant precision. It would be very strange if there was something intermediate between a constant and log, but I think it's not. Yeah?
So I understand, so in that last line you could write log of the Kolmogorov complexity?
Yeah, you can write here log of Kolmogorov complexity of all string. Yeah, you're right. Well, if we have this parallelism between Shannon's approach and Kolmogorov's approach, probably there should be the third part of this parallelism, the third parallel line with combinatorial inequalities. But yes, indeed, it is the case. But I will not talk anymore about combinatorial interpretations because it would be too. It's difficult to trace all the three lines in parallel. So there are, in fact, there are several versions of translation of information inequalities in the combinatorial language, but we will not discuss them here. Well, since we know now that the basic laws of information, these linear information inequalities, are the same for Kolmogorov, for Shannon, and even for Hartley, then probably we should try to understand the meaning of all these inequalities, what they are all about. And for the standard inequalities, it's quite simple. For example, this monotonicity inequality, basically it means that the conditional entropy is non-negative. Or this subadditivity inequality means that the mutual information is non-negative. It's everything is quite intuitive here. This inequality looks more tricky, but again, it means something very simple and very clear. The mutual information between the conditional mutual information is always non-negative. Of course, you can take sums of these inequalities, or you can substitute some tuples of variables instead of alpha, beta, and gamma. You can say that the mutual information between these 2 variables and these 5 variables, given these 10 variables, is non-negative. It's all the same. Well, and what I will spend 3 minutes on advertising the idea of drawing diagrams. I learned it probably from Young's book, A First Course of Information Theory, and it's really very useful to draw the meaning of these inequalities in the pictures, just simple standard Euler's circles. For example, yeah, the idea is that I will draw these circles corresponding to entropies of random variables. So we should understand it somehow metaphorically. So these 2 circles correspond to the measure of information, not to the blocks of bits. So in this picture, entropy of A is the first circle, entropy of B is the second one, entropy of the pair is the area of two circles, and then this part is the conditional mutual information. This is, excuse me, this is the conditional entropy of A given B. Yes. This is the mutual information. This is for a triple. This is a conditional entropy of A given BC. Again, a mutual information, a conditional mutual information. This is in red because it's quite a special part. In some books, it's denoted as the mutual information between the triple, and it is special because it's maybe negative. For some distributions, it could be negative. Okay. So we have several standard Shannon's inequalities.
Excuse me, is there a meaning for the extent at which it's negative? I imagine when it's negative, the section is empty, right? But is there, if it's -1 or -2, is there some intuitive meaning?
It's difficult with intuitive meaning, but it's simple to construct an example. You can take, for example, binary values A, B, and C such that the sum is 0 modulo 2. Then the diagram would be like this. We have -1 here, 1, 1, 1 here, and here are zeros. So it's clear that you can take something negative here. Yeah.
I like to think that the problem here is that, you know, when you have this analogy with sets and volumes, then you get the analogy between set disjointness and independence. But unlike disjointness, where if you have several sets, they are pairwise disjoint, then they are disjoint period. This is not true for independence. You have pairwise independence and three-wise independence, and they are different.
Well, so the natural question: do we have anything else, anything beyond these standard Shannon's inequality? And I guess most of you know the answer. Yes, there exists something. There exist inequalities that are valid for Shannon entropy, and that cannot be represented as a combination of basic inequalities. And quite surprisingly, it was found, at least it was published only 50 years after Shannon's original paper. And here is the very first example of a linear information inequality, which cannot be reduced to Shannon's basic inequalities. Probably I should ask there, how many people in the room know how to prove this inequality? All right, then we can spend a few minutes. It looks very strange, but it's rather simple to prove it. So when you know that it is true, it becomes pretty simple. First of all, I will write a slightly more general version of this inequality. The mutual information between A and B is not greater than the mutual information between A and B given X, A and B given Y, the mutual information between X and Y, and three additional terms. Mutual information between A and B given C, A and C given B, and B and C given A. If you identify C and X, you get exactly this inequality on this slide. So what is special in this inequality? Here you can split all variables into two groups, or into three groups: A, B, C, and XY. And in each term you can find either A, B, and C, or A, B, X, and Y, but you can never find C together with XY. And we will use this special property. Now, some claim, I will not prove it, you have to believe me. If I add here this term 3 times the mutual information between C and XY given AB, then it becomes a Shannon type inequality. It can be represented as a combination of a few Shannon type inequalities. It's easy to verify. It's quite boring, but it's simple. And now it turns out that when we have this inequality with this additional term, we can cancel it. Indeed, assume we want to prove the original this inequality for some distribution A, B, C, X, and Y. I will change the distribution. I will construct a new distribution A prime, B prime, C prime, X, Y prime, where C and X, Y become independent given AB. Just I keep the old distribution for AB, and then I choose C and XY independently given the fixed value of A and B. And notice that in the new distribution, all these terms except for this orange one remain the same, because in each term can involve only A, B, X, and Y, which remain the same, or A, B, and C, which also remain the same. So in the new distribution, all Y terms are the same, and the orange term is just by construction, it's 0. And by this mystical trick, we have proven the original inequality.
But you should then explain even more mysterious things, why it was first found in a special case where exactly this argument cannot work because C is not identified with X and everything is
I cannot answer this question. You should ask the authors, Zhang and Yang.
And how did they prove that?
They use the same proof, but this trick with this independization was hidden in the argument. So they explained the same things, but not with the English words, but with formulas. So it was a really mysterious. Yeah.
I was going to ask, is this the simplest example that you know now?
First, there is no non-Shannon type inequalities with 3 variables. It can be proven that with 3 variables, there is nothing non-classic. With 4 variables, I think it's the simplest example. Or technically, here it's with 5 variables. Well, with 5 variables it becomes simpler. And it seems that all known inequalities, all other non-Shannon type inequalities, are proven using the same technique. Maybe it's formulated in slightly different ways, but it's every time the same trick.
Is there a way to formalize, take the Shannon axioms plus this trick?
Yeah, so
Yeah.
it's just a very formal inference rule, and why we can formulate.
Yeah, you can write a program which searches over all inequalities, tries to apply this inference rule, and verifies whether the new inequality is really new.
Do those rules plus this trick then capture all possible?
We don't know. Yes.
Yeah, my question is maybe stupid, but I'm really curious. So, I mean, you just said that this inequality plus the orange term
Yes.
is a Shannon type inequality, and you can prove it the Shannon
Yeah.
bias.
Yeah.
But this observation of introducing, conditional independence because of blah blah blah, that is also a Shannon type argument. So, what does it mean that an inequality is not Shannon type?
Well, when I say non-Shannon type, well, people say non-Shannon type, then they mean that this inequality cannot be represented as a linear combination of basic Shannon's inequalities. Just a linear combination with positive coefficients.
So you don't mean that this Shannon can never prove this, no? Of course.
Yeah, sure.
The technique is quite
So it seems that people from this area, when they write non-Shannon type inequality, they mean exactly this, that some inequality is not a linear combination of basic inequalities from Shannon's paper.
It's just a formal thing, not
Okay. Well, since '98, people went on some other examples of a non-Shannon type in this specific sense. Information inequalities, actually quite many are the examples. Technically, infinitely many are the examples. And František Matoš actually proved that for each n greater than 3, the class of all information inequalities is not polyhedral. That means that it cannot be reduced to any finite family of basic inequalities.
in terms of addition.
In terms of linear combinations, yes. In terms of linear combinations, not in terms of this trick, yes. Well, okay, I will skip this discussion of applications. Just a funny fact: we have infinitely many formal linear information inequalities. Well, let's look at another example. It's a simple statement about Shannon's entropy. It could be an exercise, some textbook on Shannon's entropy. It's again an inequality, but it's an inequality with some constraints. This statement claims that if we have a distribution A, B, C, such that these three terms are zeros, then we have these specific linear inequalities. So this inequality is not valid for Shannon entropy in general. You can invent a counterexample. But under these conditions, under these constraints, it becomes valid. And since I advertised the idea of parallelism between Shannon's and Kolmogorov's cases, now it's natural to ask ourselves, can we prove something similar for Kolmogorov complexity? And in fact, it becomes not that straightforward. First, I want to explain the idea of a proof of this exercise, how to prove it. It consists of two steps. The first step is, I think it's an exercise from Chisar and Körner's textbook. If we have this condition with three zeros, then we can extract the mutual information, the part for this middle thing, as a specific separate random variable. So technically, this W, you can think of it as, for example, as a distribution on C given AB, or a distribution on C given A or given B. If you have a value of A or a value of B, you can compute this W. And in fact, it's easy to verify that all these equations hold here.
And if this W is this common information in this sense, then all the conditional information, A and B given X and A and B given Y, can be replaced by W.
Yeah, you anticipated my next formula. Indeed, when we extract this W, we can write a Shannon type inequality for this W and observe that it's exactly the inequality we wanted to prove.
It's funny, we don't have W, we don't have X and Y in the condition, and we don't have C in the conclusion.
Yeah. And when you want to prove a similar statement for Kolmogorov complexity, you're in trouble because the first step fails. In Kolmogorov complexity, there is no conditional distribution of this sense, and it's not clear how to extract this W. And in fact, even probably before that, you should ask ourselves how to formulate this statement for Kolmogorov complexity. Probably like this. If the three mutual informations, the conditional mutual informations, are logarithmic, because it's the best possible reasonable precision Kolmogorov complexity, if they are logarithmic, then we have the concluding inequality also with a logarithmic precision. So now the question is, now we have a statement, a conjecture, and the question is how to prove it. But before we will try to prove it, just observe that, okay, we know that logarithmic term is the most natural in this context. But a priori, you could ask about other precision. So you could write the square root of n or something. But when you write such a conjecture for Kolmogorov complexity, you probably should ask yourselves, can we prove something similar in Shannon's case? Can we prove a kind of conditional equality for Shannon's entropy with some soft constraints, where the three mutual informations are not exactly zeros, but something small? Then the proof from the previous slide doesn't work, but maybe some other proof would work. And in fact, it is the case. So it turns out that this conditional inequality for Shannon's entropy can be proven like that. So an alternative proof of this conditional inequality in Shannon's framework. First, we prove a non-conditional inequality for the mutual information by for Shannon's mutual informations by coincidence. It's exactly the inequality on the blackboard. Yes, we already know that it is true. And you see, if these blue terms are zeros, then we have the resulting inequality, the inequality that we wanted to prove. And we know that non-conditional inequalities can be translated in the language of Kolmogorov complexity. So we write this inequality for Kolmogorov complexity with a logarithmic precision and conclude that if these blue terms are logarithmic, then the original inequality also valid for Kolmogorov complexity with a logarithmic precision. Okay, so somehow we reestablished the parallelism between Shannon's entropy and Kolmogorov complexity. But probably we're not quite satisfied, because in the original proof for Shannon's entropy, we got something better. We extracted this mutual information between A, B, and C. And in the new proof, it seems that we have some formal manipulation with, yeah?
So, sorry, step 1 required that C and XY be conditionally independent given AB, right?
No. Step one is unconditional information equality, which is valid for any distribution.
No, but first we assume we prove it for independent, and then everything can be reduced by this case to this case by artificially making them independent and noting that it doesn't change the quantity. So this was a strange trick.
Yeah, all the idea is that this white inequality without a red, this orange part, it is valid for any distribution.
With red it's weaker and Shannon type, but still, strangely, the general case can be reduced to the weaker case by strange trick. This is what is.
Okay, so what I'm complaining about, that now we lost this property of extracting the mutual information. So there are questions, can we, first, in Shannon's framework, can we extract this mutual information if the constraints are soft? And another question, can we do something similar in Kolmogorov's framework? Yeah?
Can you explain what the W was? It seems like explicitly.
So once again,
I mean, like, can you say, can you define W?
okay, you can define W as a conditional distribution on, say, C. I break the symmetry on C, given A and B. Or technically, you can say that you define classes of equivalence for values of A and values of B. Such two values are equivalent if they give exactly the same conditional distribution on C.
So it actually does not define, given not A and B, but given some specific values for A.
Okay, yeah, given values of A and B, yeah, sure. Just what is a conditional distribution? It's a conditional distribution on C given values A and B.
So it's a function of A, B.
Yeah, so wait. Yeah, it's by the definition, it's a function of A, B. And this 0 explains that it's in fact a function of A. You don't need B to compute it. And this 0 explains that it's in fact a deterministic function of B. So you can compute W given either A or B. You don't need to know both. And a similar argument explains that assuming this 0, you can extract the same W also from C.
No, it's not. The same W, it's a bit...
The same. Just.
Given C, okay, define that.
Yeah, it's a very special case when we have these three zeros. Okay, so the question is, what can we do with this extraction of the mutual information when the constraints becomes soft, when we have epsilons instead of zeros? Of course, this property of extracting W is very fragile. If you perturb slightly the distribution, it will be broken, and formally, naively, the statement is not true anymore. But in some sense, it becomes true. And in some standard sense, in fact, you should do this trick of serialization. You should take n independent triples with the same distributions, and then it turns out that you can find W, which almost extract this mutual information from this serialized A, B, and C. And the proof of this fact is also quite standard. It follows. Okay, I will call it Ahlswede-Körner lemma. In fact, it's a simplified version of Ahlswede and Körner's theorem. But for our applications, we need it only in this simple form. If we have n independent identically distributed copies of A, B, and C, then we can find W which corresponds to this red area. Somehow this W, it knows the same thing about A, about B, and about the pair AB, the same things as C. And at the same time, this W is a part of AB. It can be extracted directly, deterministically from A and B. And if these three guys are epsilons, then this Ahlswede-Körner lemma will give exactly what we need. And we will get this conclusion. We'll get this conditional inequality with which becomes true with some small residue term if the constraints are valid also with some minor violation. And in fact, if you do all the calculations quite accurately, then this conclusion becomes even more precise. We will get exactly this inequality. Again, exactly the same inequality as this Zhang and Yang. So somehow meditation on the parallelism between Shannon's and Kolmogorov's framework plus this simple exercise from a textbook plus the known theorem by Ahlswede and Körner, they all give us an alternative proof of Zhang and Yang's non-classic inequality. So somehow we can prove the same inequality without this strange trick with this fake orange term. Yeah.
So I think I lost you somewhere. So how did you go from n to not no repetitions?
First, I have some A, B, and C. I take n independent, identically distributed copies. Now I look A, B, and C, and well, I didn't prove it. It's not terribly difficult in this form, this simplified version, but it requires some argument. Then we can find this W, and this W is not serialized. This W is jointly distributed with the serialized A, B, and C, and somehow it extracts the mutual information. On the picture, it's not symmetric, but the three parts that make it non-symmetric, in our assumption, they are negligible, they are epsilons. So this red part is more or less this middle part. And when we when we make this intuitive argument formal, then by miracle we get again the same Zhang and Yang's non-Shannon type inequality.
But it's an obvious thing. You can prove the equality for serialized variables because they are just multiplied by n. So strangely, to prove an equality, we need to go to serialized version and then take the limit as n tends to infinity, I guess. Yeah.
Okay, we have these small erased terms. Technically, they are slightly greater than square root of n, but indeed they tend to 0 as n goes to infinity. It seems I should stop in 3 minutes. Yes. Okay, after this meditation, we should look again on Kolmogorov complexity. Can we also prove this property of extracting the mutual information? And the bad news is that there is no Ahlswede-Körner lemma for Kolmogorov complexity. At least it is not known. Probably it's just the statement is wrong. But somehow it can be proven that we still can extract the mutual information from a triple A, B, and C, assuming that the three conditional mutual informations are negligible. But it's not that simple. It requires some more delicate argument. And by a miracle, this more delicate argument involves as a special technical part, the principal technical part, again, the very same non-Shannon type information equality. So somehow it seems that this strange, I would say even ridiculous inequality proven by Zhang and Yang, and somehow it's connected with the idea of extracting of the mutual information from a triple. Well, what can I say in 2 minutes? Okay. There are the cases when the things are not that good as above. There is another non-Shannon type, another conditional inequality for Shannon's entropy. This is an example of a conditional inequality proven also by František-Matuš. If the two mutual informations are zeros, then we have again the same resulting linear inequality. And for this inequality, there is no unconditional, no corresponding unconditional inequality for entropies. That is, it would be natural to conjecture that something like that is valid for entropies with some coefficients lambda, but it turns out that whatever are the coefficients lambda, we can find a counterexample. So somehow there is no soft constrained version for Kolmogorov complexity for this inequality. But by miracle, for Shannon version, yes, for Shannon version. But by miracle, we have something similar for Kolmogorov complexity, but not with a logarithmic precision, but with some different strange precision, something like it's written here.
Stronger precision in the condition doesn't improve that.
You can choose a condition in the constraint, and then it will determine the condition in the conclusion. And okay, just another peculiar example. There is another conditional inequality which is valid for Shannon's entropy, which has no unconditional counterpart, and which has no counterpart for Kolmogorov complexity. In Kolmogorov's case, even if you take the strongest possible constraints with logarithmic precision, the resulting inequality can be false in the strongest possible sense. And I think I have to stop here.
So any questions? Can you just show fast all the slides?
All the remaining slides. Okay, okay. It's about extracting another part of the information of this picture. So can we extract this A minus B? In Shannon's case, it somehow corresponds to the classic slepian-wolf theorem. And in Kolmogorov's case, it's the theorem, well, usually it's called Muchnik's theorem, but I think the first proof was in this Bennett, Gatch, Levitani, Zurich paper. And this afternoon, Mario Zimond will explain how to formulate it properly in Kolmogorov's case, and why it is valid for Kolmogorov's case, and which version are true, which are not, etc. And some similar statement when you want to extract two conditional descriptions are valid in Shannon's case, but not in Kolmogorov's case, somehow strangely. And it's all corresponds to some difference between combinatorial interpretations of Shannon's entropy and Kolmogorov's complexity, but it requires more time. But this slepian-wolf theorem in the context of Kolmogorov complexity, it will be explained this afternoon by Marius.
Yeah. Okay. So any other questions? So I have two historical comments. First, this inequality for volumes, which you indeed was mentioned in our paper with Hamner, but I think it's called shear inequality for more general cases called shear inequality, and I think that somebody know the entropy proof before. Just we didn't know this, but probably the entropy proof was earlier. But I don't know. Somebody maybe knows the history. And second, there is a paper of equivalence that the linear inequalities are the same for Kolmogorov complexity and Shannon entropy. And so you also mentioned some paper with several authors, but it's your result. So
well, in this equivalence theorem, there are two directions. Both directions, right. Yes, one direction was proven by Sasha, and he calls it trivial, and I proved another one.
Definitely was always known. Okay.
But anyways, it was published in our joint paper, so you should take the responsibility.
This is not. You should not shift the responsibility. Okay. Any other questions or comments?
Yeah. About children's inequality in the preschool in Sin, someone told us that it's called Hans inequality when it is the generalization to any n. So I doubt now whether
Schiller is more complicated, but the question is whether the entropy proof was well known folklore and how long it was known. So, but it's indeed.
No, and another historical question is why this non-Shannon type inequalities was not proven somewhere in Hungary in 1970s. Or maybe the people proved it, but they didn't bother to publish it because it's too simple. It seems that all the technique were ready in the 70s.
considered non-Shannon, so I don't see why we should prove it.
No, just that's not a question of the name. It's a kind of interesting new tool. This either this strange trick with making things independent, or a strange trick of serialization before proving inequality, which is also actually some kind of inequality, but logarithms. But still, you need to do something very strange to prove it, instead of using some properties of logarithm. Okay, let's think. So the next starts when exactly?
25, 11:25.
1925.
11:25. Yes.
11, sorry. 11:25.
My